Over the past few years, drones have become a very popular gadget and serious hobbyists alike. With the development of the technology, drones are becoming more and more easier to control. The first generation of the drone is actually very hard to control because it does not have the key part, which is the flight controller. It's like the brain to the human, so the player needs to fly it manually. At that period, it's not even called as a drone, more like a RC plane, which is remote control plane or remote control helicopter. So as you can see from the video clips, the RC helicopters are hovering. At least the pilot is trying to, but it's still not stable. That's because it does not have the flight controller. Inside the remote controller, there are different channels, usually 3 or 4 channels. Each channel controls single movement. For example, moving back or forward, which is the throttle. Similar thing also happen in the real helicopter. When you are flying one, you yourself are acting as a controller. In the video,
Left pedal. Oh, it's like R22, like the right skid will come first. Yeah, exactly the same.
as you can see, even after hours of training time, I still cannot hover the helicopter that good. The chopper is a little bit drifting, but control can be more accurate and precise with more practicing time. As a contrast, the drone can do the hovering quite good, actually very good. You can see in the video that after taking off, without my control, the drone can still hover by itself.
This one is hovering by itself without any control and it's very stable. Also, if I try to drag this drone, it should be able to return back to its position, but I'll give it a try. So look, let's go back to its original position.
This can be done thanks to the existence of the flight controller. So today what I want to emphasize is the importance of the flight controller, the PID control behind of it, and eventually how it is possible to achieve the hovering status. In contrast to terrestrial mobile robots, for which it is often possible to limit the model to kinematics, the control of aerial robots require dynamics in order to account for gravity effects and aerodynamic forces. Since quad-rotor flying robots use 4 rotors instead of 1 rotor to provide thrust to the robot, it has 4 input forces and 6 output coordinates. Thus, the payload capacity is larger compared to the conventional helicopter. In general, existing quad-rotor dynamic models are developed on the hypothesis of a unique rigid body, which is a resistive that does not account for the fact that the system is composed of 5 rigid bodies, 4 rotors, and a crossing body frame. A quad-rotor is an under-actuated aircraft with fixed pitch angle, 4 rotors, as shown in the figure 1. The aim is to develop a model of the vehicle as realistically as possible. In the quad-rotor, there are 4 rotors with fixed angles, which represent 4 input forces that are basically the thrust generated by each propeller, as shown in the figure 1. The rotation direction of 2 of the rotors are clockwise, while the other 2 are counterclockwise, in order to balance the moments and yaw motions as needed. The collective input μ1 is the sum of the thrust of each motor. Pitch movement is obtained by increasing the speed of the rear motor while reducing the speed of the front motor. The roll movement is obtained similarly by increasing the speed of right motor while reducing the speed of the left motor. The yaw movement is obtained by increasing the speed of the front and rear motors together while decreasing the speed of the lateral motors together. This should be done while keeping the total thrust constant. Neglecting the air resistance, the dynamic model of the quad-rotor helicopter at a small angle can be obtained via a Lagrange approach. The equations of the motion can be written using the force and moment balance. X, Y, Z represent the coordinates of the UAV's center of mass in the initial coordinate system. Phi, theta per c represent 3 inclined angles of the quad-rotor. M is the mass of the UAV, B is the lift coefficient of the propeller. Tau phi, tau theta, tau per c are the yaw moment, pitch moment, and roll moment. Omega is the angular velocity of the 4 rotors. When the quad rotors are hovering, theta and phi are close to 0, the flight height is approximately satisfied. Using the omega to represent the angular velocity at each propeller when the UAV is in equilibrium. At this moment, z equals to 0. Therefore, we get equation 3. Substituting equation 3 into equation 2 gives equation 4. Recording UAV's control input as equation 5. In the above equation, the value of the K0 is related to the output signal duty cycle. By union, equation 4 and 5 gives equation 6. Let K equals to K0 times B divided by M. By applying the Laplace transformation to the equation 6 gives equation 7, which is the transfer function of the quad-rotor system in hover mode. From the equation 7, we can see that the controlled object in the flying height control system of the quad-rotor is the second-order integral process, so the PD controller is the choice. The real-time altitude of the quad-rotor was measured by barometer, and its time delay was recorded as TAF1. According to reference 16, the transfer function of the barometer can be expressed as equation 8. At this point, the UAV's hover flight control block diagram is shown in the figure 2, among which the transfer function of the PD controller is equation 9. The system's open-loop transfer function is equation 10. Its closed-loop polynomial is equation 11. The expected characteristic polynomial of a closed-loop system for a typical third-order system is equation 12. Combining equation 11 and 12 gives. From the reference, we can see that the optimal response is obtained when the damping ratio of the system is 0.707. Name this PD controller PD1. Recording the time delay of the quad-rotor central processing unit as TAF2. The control block diagram is shown in the figure 3. The transfer function of the PD controller is equation 14. The system's open-loop transfer function is equation 15. Applying the first and second derivative to equation 15 gives equation 16. Equation 15 can be expressed as equation 17. Apparently, when lambda equals to minus a, we have delta s equals to 0. The first and second derivative of delta s is 0. Applying those values to the equation 15 and 16 gets equation 18. However, the actual values of TAF1 and TAF2 are depend on the sampling frequency of the sensor and the processing speed. They can be measured experimentally. We call this PD controller PD2. By using the UAV model used in the reference, the relevant parameters of the UAV are m equals to half kg, b equals to 1.12 times 10 to the minus of 6, k0 equals to 1 times 10 to the power of 4. Taking TAF1 as 0.16, TAF2 as 0.12, so we get the proportional gain and differential gain of the PD1 and PD2. The controller parameters of PD3 are from the reference. The quad-rotor with the same parameters is controlled with different PD controllers simulated in the MATLAB. In order to evaluate the control performance of each PD controller using different forward and reverse excitations as the simulation inputs, which is the desired height z. First, at T0, inputting a positive magnitude 5. At T15, inputting the reverse step signal of amplitude 2. Second time at T0, inputting a positive magnitude value 10 and reverse input signal 2 at T15 second. From the simulation results in figure 4 and 5, all the controllers have fast response time. When the set hovering height is low, the robustness of PD1 and PD2 is slightly better. However, when the hovering height is higher, the overshoot of both increases or even exceeds the amplitude of PD3. This is because the output of the drone's motor can be limited during the actual flight, and in order to ensure that the UAV's rising and descending speed are not too fast, a saturated controller that limits propeller thrust is usually added between the PD controller and the controlled object. but such design can easily cause overshoot in response and reduce system stability. In order to suppress the response overshoot caused by input saturation, a speed limit compensation part is added between the PD controller and the controlled object. At this point, the simulation results are shown in the Figure 6. Regulation PD control step response based on kinetic model. In this video, the dynamic model of the cross-type quadrotor under hovering flight was linearized, as well as its linear mathematical model. The dynamic characteristic of the system with sensor time delay and processor time delay are analyzed, respectively. The proportional gain and differential gain of the PD controller are calculated based on the expected dynamic characteristics. The speed limit compensation part is designed for the response overshoot caused by the input saturation. The simulation results show that the designed PD controller has a good dynamic response, and the introduced speed limit compensation can effectively restrain overshooting and improve the stability of the hovering flight. The method used in the video controller parameter tuning in this video is also suitable for the PD controller design of other types of aircraft.